Welcome. Here's another lecture, and this one is on the electric force and the electric field. Let's go ahead and get started. Okay, so today we're going to talk about field vectors from field lines. And first off, here's a couple of rules. The electric field at any given point is not the field line itself, but it can be determined from the field line. The electric field vector is always tangent to the line of force at that point. And finally, vectors of any kind are never curvy. Well, what does this mean in practice? Let's go ahead and see here. So, this is a positive charge. And let's say I put my small positive test charge right there. Okay. The electric force or the electric field from this positive charge would be directed away. Okay, and then the electric field line or electric field vector from this negative charge would be directed towards the negative charge. It'd be a little bit smaller because of the distance. Okay, so now the electric field vector at this point is the superposition of these two individual vectors, or another way of saying that is we add those two vectors together. So I'm going to use the parallelogram method for coming up with a resultant vector here. So parallelogram, just make a parallelogram out of this shape, and the electric field vector at that point is right there. Now, let's draw another one. Let's do a similar right up here next to, in the similar position, but above the negative charge. So at this point right here, the negative charge is going to create electric field line directly towards it, or electric field vector directly towards it. And the positive charge is going to have a component, or give it a component away and shorter because of the distance. So again, using our friendly neighborhood parallelogram, that would be the electric field vector there. If we put one in here, the positive would be fairly strong and going towards the negative, and the negative would also cause one to be going fairly strong and towards it. So we would add those two vectors together and we would get the resultant, which would be larger. And we could do that all around these charges. So what does that mean? Well, that means that when we get up to this point in space, our electric field line is following in the direction of our electric field vectors. Okay, right there. Another example. And there's symmetry for this charge distribution, so I can reflect everything for the lower end, and I can also do it in the middle and on the outside. So this is a electric field line diagram that is generated from looking at what the actual electric field vectors are in the region of these two charges. And so hopefully you understand a little bit more about what's going on with those. So let's see what's up next. Okay, now we're going to talk about what the actual definition of the electric field is. And in this case, this is the symbol for the electric field. And the force that comes from electric field is equal to the strength of the electric field times the charge that has been placed in the electric field. So this is the charge on, or I'm sorry, the force that would be applied to that charge by the electric field. And that comes from the definition of the electric field. And I'm going to use the three-lined equal sign because that means is, or is defined as, the electric force experienced by a small positive test charge placed in the electric field. And this little sub-zero just means that it's a small positive charge. It's just a notation device. So again, the force is measured in newtons. The electric field is measured in newtons per coulomb. That's kind of easy to see where that comes from. Okay. A little bit later on, we're going to find out that there's another way of writing the units for the electric field, and that will be volts per meter. Either are correct. This is more common for right now. A little bit later on, when we get into what electric potential energy is, we will use this form. Charge again, Q, is the amount of charge on the particle or object, and the units are coulombs. We have our 400 microgram styrofoam bead. It has 600 excess electrons on its surface, and we want to know what the magnitude and the direction of the electric field that's needed to suspend it in midair. Okay, so let's go ahead and draw our picture. Here's our bead, and it has excess electrons, so I will make it a negative charge. And we want to know what the electric field is. Well, I'm assuming up on the slide is in the up direction, so we would need an electric force in the upward direction to hold it. And that's the force from the electric field. And gravity would be pulling this styrofoam bead down. So there's our free body diagram. Now we just have to put that together. We want it to be suspended, so that tells us that the acceleration is 0. So let's go ahead and write our Newton's second law equation for this. The sum of our forces is equal to 0, and is equal to the electric force, which is pointing up, minus the weight. Okay, so the electric force has to be equal to the weight. So that has to be equal to 400 micrograms, which is 400 10 to the minus 6 for the micro. We need to get it to kilograms, which is 10 to the 3. So we need to turn that into 10 to the minus 9th kilograms. Times gravity. The acceleration due to gravity is 9.8. Okay, so that should give us our electric force that we need. Well, what does that need to be equal to? Well, the electric force is also equal to the electric field times the charge. Okay, well, we're looking for what the electric field is. The electric field is equal to the force, the electric force, over the amount of charge. Well, I guess let's talk about what that charge is. It's the same as what it was in our previous problem. 600 electrons times a negative 1.602 times 10 to the minus 19th coulombs per electron. Okay, so I think you can do this to come up with the electric field strength, the magnitude, we'll say. Let's make that clear. we also need to know what the direction is of the electric field. Well, the challenge here, or the place that we're going to catch you in a mistake, is realizing that the electric force and the electric field directions for negative charges are opposite. So if we want an electric force on an electron up, our electric field must be down. Okay? All goes back to the definition of the electric field. The electric field exerts a force on a positive charge in the direction it's pointing. Opposite direction for the negative charge. Well, let's see what's next. What's the charge on the bead? It has a mass of 32 milligrams. Well, this is a great problem because it brings us back to making vector force diagrams on our charge here. So on this charge, there would be a force to the right because something has to be suspending it or pulling it out from the wall. There has to be a force along this string, and there would have to be a force pointed down. Okay, because there's gravity, there's tension, and then there's also the force from the electric field. Okay, so this is a classic Newton's second law, write out the equations, solve for the unknown. So some of the forces in the x direction, acceleration is going to be 0 because it is in static equilibrium. And that's equal to, in the x direction, we have the electric force, and we have, in the negative x direction, the x component of the tension. So we can say that the electric force is equal to the x component of the tension. Now, using the electric field, which has been given to us, to find the electric force, it would be E times Q, which is what we're looking for. We're looking for that Q right there. That's equal to the x component of the tension. Well, the x component is opposite of the 40 degrees. X is opposite of 40 degrees, so that goes with sine 40 degrees. Okay, well, I don't know what the charge is, and I don't know what the tension is. So I'm going to need another equation. Sum of the forces in the y direction equal to 0. Again, it's in static equilibrium. And that's equal to forces in the up direction, or the positive y, which is the y component of the tension, minus the weight, m times g. Okay, so that means the y component is equal to the weight. So the y component is the tension times its opposite of, or I'm sorry, it's adjacent to the 40 degrees. So that's cosine 40, which is equal to mg. So the tension is equal to mg over cosine 40 degrees. Now, it just becomes a matter of substituting and solving for Q. So Q is equal to T sine 40 over the electric field, which is T is mg over cosine 40 times sine 40 over the electric field. I think you can take it from there. Thanks for watching.